So this next set of videos will be on somatosensation, which if you remember, the root word soma means body. You can see it's just body sensation, the body senses. So this first video is going to talk about all the ways we pick up somatosensory information and transduce it into neural signals. Then the next video will get into the neuro-brain side of things. And then after that, the next video after that will dive into touch perception in more depth. So the somatosensory system, it's really a bunch of different sensory systems, all of which feed into and help construct perceptions about our body and its status, its posture, how it's changing, and everything else about it. So under the umbrella of somatosensation, we would actually include all of these things. So the first is the one that seems most obviously, related to our body sense, and that's touch. One of the classic five senses, right? So touch is really, usually it's some combination of pressure or vibration that we're sensing. And the way that we pick those up is through actually little receptors that measure mechanical stimulation to our skin. So the pressing against it, the vibrating, that's a mechanical action, and it mechanically activates these little sensory receptors we have for touch. So we sometimes call it mechanoreception, the traditional sense of touch. However, there's other body senses, other things that we can experience through our body, right? So there's pain, often called nociception. We'll talk about that. There's temperature, which might be called thermoception, or sometimes you'll see it written as thermoreception. And then there's our sense of our insides or gut sensations, right? What's going on inside your body. We can definitely feel that. And that's called interoception, for being right inside of you. And then there's a couple others, which we won't really cover in detail in this video, but our position of our body and its parts falls under what's called proprioception, things like our current posture, whether my arm is up or down, things like that. And then balance or our sense of motion, our sense of acceleration, things like that would fall under the fancy name equilibrioception, but you might just think of that as kind of our sense of balance or sense of balance and motion. Now, in this video, we'll dive into those last two ones in a future topic of their own. So in this video, for this moment, we're just going to focus on these first four. Before we start, though, I wanted to pose a simple trivia question. What is the heaviest organ in the body? Think about it for a moment. Think about different organs. And it's kind of a trick question unless you actually think about the fact that the skin is an organ. The skin is actually the heaviest organ in the body, right? It's all over. There's a lot of it. And what skin is basically there to keep fluid in, right? And to keep germs and dirt out, to not get inside our body. And when you look at the skin in a little more detail, there are different layers. There's an outer layer called the epidermis, which is basically just dead skin cells, and it acts as a barrier, right? It has that barrier function. But below that is another layer called the dermis. And the dermis is really important. It provides some cushion when you kind of push in on your fingertips, things like that. But more importantly for us, it has lots of sensory receptors there in the dermis of the skin. Now, when you think of sensory receptors in your skin, you're probably going to think first of receptors for touch, right? And touch receptors are actually called mechanoreceptors. So the sensory receptors for our touch system are called mechanoreceptors, and that's because they're activated from mechanical stimulation like pressure and vibration, as opposed to like the sensory receptors in your eyes, for instance, the rods and cones. Those respond to light, not to mechanical stimulation. Okay, and then in these touch receptors, there are four types of mechanoreceptors that give us our basic touch information, and all of them send signals to the brain using myelinated axons. I mentioned that idea in passing in our last topic when we covered neurons, but myelinated means there's myelin sheath. It's a covering along the axon of some neurons, which makes the electrical signal travel faster and more efficiently down the axon. So touch information from these mechanoreceptors, it goes to the brain very quickly relative to some other types of sensory input. Now, let's see what those four types of mechanoreceptors are specialized for. First off, there are going to be two of them that are close to the surface, close to that outer epidermis layer. And both of those start with an M, so maybe you could remember them as M for they're mighty close to the surface or something like that. But the two we'll talk about here, there's Merkel discs near the surface and there's Meissner corpuscles near the surface. Okay, so the first type, and the one we'll probably focus on the most in the coming videos of somatosensation, is these Merkel discs. They're named because the tip of the neuron, unlike the dendrite end, the tip that picks up input from the world, is shaped like little discs. So they're really good at detecting pressure, especially static pressure, like, a certain amount of force is on my skin right now. I can measure that. So they're measuring how much force there is. They help us perceive a lot of fine details, texture, shape. Like if they're not working, we have a lot of trouble with those functions. Then there are the Meissner corpuscles, which have a different shape, a different ending where their tip receives input from the world. So they'll kind of like this. And again, that'll connect to a cell body, which then connects to these axons that go very far. These sensory receptors are better for detecting dynamic pressure, meaning changes in pressure, like when stimuli show up or disappear, increase or decrease. And functionally, that's important for things like maintaining grip or detecting motion on your skin, things like that. Now, there is an important difference between how these two touch receptors work, and that's that Merkel discs are what we call slow adapting, meaning they keep firing as long as the pressure is still there. A single Merkel disc might keep sending pew, 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 pew to the brain while there's something pushing against your skin there. Basically, they don't tire out very easily. On the other hand, Meissner corpuscles are what we call rapid adapting. They do kind of tire out quickly. They fire like crazy when something changes, like when a pressure begins or ends or gets more or less intense. They tell the brain about the change, but then they shut up. They stop firing until some other change happens. So if something is just pushing against your skin without any change, the Meissner corpuscles won't be firing much. That's why I say these are better for detecting dynamic pressure, while Merkel discs are good for static pressure. You can kind of see that in the diagram here. The blue line would be the actual turning on of the stimulus. In other words, some pressure is added to our skin. Something starts pushing on your fingertips, right? The Merkel discs, as long as the pressure is still there, the Merkel discs are going to keep firing beep, 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 the whole time, whereas that exact same stimulation, where you start pressing on the fingertip and then after a while you stop pressing, the spikes, the action potentials or neural firing of the Meissner corpuscle, if we're measuring that, would show some activity right when the stimulus showed up, and then it would adapt quickly and stop firing. It's like, okay, I'm tired of it. Like nothing's changed, nothing's interesting. I don't have to keep firing. I don't have to keep telling the brain anything. But then when some change happens again, like when it stops being there, when there's a change from the stimulus going away, the thing that was touching our skin isn't touching it anymore, then this will send a signal to the brain about that change. But once again, it then rapidly adapts. It rapidly stops firing to that new situation. Okay. So that was 2 of the 4 mechanoreceptors that give us touch information. The other 2 start with letters deeper in the alphabet, you might say, P and R. So the letters are kind of deeper in the alphabet, and these little mechanoreceptors are deeper in our skin, lower in the dermis. So that might help you remember those 2. So they're a little further down in for these, okay? Now, like the other touch receptors, they're neurons. They're a specialized type of neuron. They're sensory receptors, so sensory neurons, meaning they have specialized endings on the dendrite side of them, specialized in special shapes that help them detect certain mechanical input to the skin. So first, there are Ruffini corpuscles, sometimes called Ruffini endings, and these guys are really good at detecting skin stretch. Like when the skin stretches, it literally stretches these little endings and opens ion channels to make that neuron fire. And functionally what these are good for, they're helpful for things like controlling your finger position and movement, for tracking, how tight your grip is as you're holding a water bottle, things like that. Then finally, there are Pacinian corpuscles. These little mechanoreceptors are deep in the skin, so they help detect dynamic changes in deep or gross level pressure, like pressure on your skin that affects a big, wide area. But also, and more importantly, they're great at detecting vibrations, which is important because it's mostly through vibration that we're able to feel fine textures, like whether something is kind of smooth or rough, hard or soft, whether something's metal or wood or whatever. Vibration info is a big part of that, and that comes from, it's detected by Pacinian corpuscles. I'd say these and the Merkel discs we talked about first are the two most interesting ones that we'll hit on in some more depth during this somatosensation topic. Now, just like the Merkel discs and the Meissner corpuscles before, one of these is slow adapting and one is rapid adapting. Specifically, those Ruffini corpuscles that detect skin stretch, they're slow adapting. So as long as the stretch is still happening, the neuron will keep firing pew, 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 to the brain. When the stretch stops, the neuron will stop firing. Whereas Pacinian corpuscles, they are rapid adapting. So again, they really get excited and send a message to the brain when they detect a change, like when a touch stimulus begins or when it ends, or just when it increases or decreases, like if the vibration changes, which would suggest the texture you're running your finger along has changed in some way. You've gone from a softer surface to a harder surface. The texture has changed as you're running your finger along it. Pacinian corpuscles will send that info to the brain as soon as there's any change. All right, so those are the 4 mechanoreceptors for touch information, like the traditional idea of touch. But as I mentioned, somatosensation is more than just touch. So let's talk about some other sensory receptors we've got for the somatosensory system. First off, we detect types of painful or damaging effects on our body. We detect those through what are called nociceptors, basically pain receptors. Think of noci as pain. It's our root word for pain. So nociceptors are pain receptors. They detect damage, and that can be mechanical damage from like excess pressure or deformation. In other words, getting your finger smashed under something really hard, like a rock or a vise. But also can detect thermal damage, like really extreme heat or cold, where it's damaging, or chemical damage, like from just irritants or toxins, or even spices like capsaicin, right? The heat of capsaicin. Sometimes when we're doing studies of pain, we'll actually inject capsaicin under the skin in order to turn on those nociceptors and make people feel pain in a controlled manner. And that's because the nociceptors, they send a signal to the brain. They say, I'm detecting pain. I'm detecting, in this case, chemical pain. Now, those nociceptors, they're described as free nerve endings, just meaning they have no structure at the tip. So the 4 mechanoreceptors we talked about all had those specialized endings, like those little kind of bulbs or discs or whatever shapes at the end of them to help them mechanically pick up those differences. Well, free nerve endings, like these nociceptors, they don't really have a structure at all at the tip. They're just raw nerve endings. Now, I mentioned before that mechanoreceptors for touch, they send their info to the brain using myelinated axons for a really fast signal. What about these nociceptors for pain? Are they myelinated and fast, or are they unmyelinated and thus relatively slower? And the answer here is both. So some nociceptors send their signal using what are called A-delta fibers. So by fibers, I just mean like the axons coming out. So A-delta type of fibers or axons just means their axons are myelinated and thus send signals to the brain really quickly. They're also thicker axons, which helps the information travel faster. So this would be like the initial sharp pain you feel when you stub your toe or step on a Lego or cut yourself on a sharp corner. It's also part of the reflex arc that can cause some automated response by your body really quick before you even consciously experience the pain. It's fast. So that's some of our pain signals. Some of our nociceptors are for that initial sharp, quick pain, the detecting of the pain. Oh my God, some pain happened. But there are also a lot of nociceptors with unmyelinated and thinner axons. We call those C fibers. So the type of fiber, the type of axon coming out, we call them C fibers. These neurons send their signal to the brain much more slowly. I mean, it's still fast because it's a neuron, but a lot slower than myelinated neurons that have thicker axons. So this is where we experience what's sometimes called second pain or lasting, kind of lingering pain, like the deep, lasting pain that you get for the next minute after you stub your toe or hit your funny bone, or the continued pain from the cut that you just sustained on your skin. It's less of a, oh shit, something just happened signal, like the A delta fibers would send, and more of a, hey, I'm still in pain down here, hey, I'm still in pain down here kind of signal. So it gives that experience, sometimes referred to as the pain after the pain. Now, a side note here, there are special nociceptors, kind of a special form of nociceptor, which are generally also C fiber type, that go off specifically to histamine and cause us to experience an itching sensation. So think of this like a mosquito bite kind of itch, right? There's different types of itch, but this would be for the mosquito bite type of itch. It comes from histamine. That's nociceptors sending a signal to your brain to make you feel that itch. Now, itch is interesting because it's similar to pain in some ways. It's got a negative valence, right? It's an unpleasant sensory experience. But pain causes withdrawal, right? Things that cause pain make us back away from them, whereas itching causes approach. It causes scratching. We move our fingers to the place it's itching. And some other interesting kind of side notes about itching. We won't go into a lot of detail here. I just want to mention it. But since itching and pain use the same pathways to go up to the brain, we'll see that soon, painful stimuli, like applying heat, like painful heat or chemicals or electrical shock, will actually reduce this kind of itch. I'm not saying you should shock yourself when you have a mosquito bite, but it does in fact make the sensation go away temporarily. Now, other types of itch don't involve nociceptors. There are other types of itch, but they might originate elsewhere in the nervous system. Just for example, like, taking too many opioids, you can get itch, or from multiple sclerosis, or from nerve irritation, somewhere in the nerves along the rest of your body, or itch can happen as part of a psychiatric disorder, related to like hallucinations where there's not actually any sensory neurons going off, or part of OCD, things like that. And we'll see some examples. I'll give some readings if you're interested in itch. Now, of course, when we're talking about feeling pain, you might wonder about, well, what about pleasure, right? Pleasant touch. And actually, pleasant touch is really interesting. First off, it's got important functions socially for bonding, either like a caregiver-infant bonding, or maybe even a pet owner-pet bonding, but also partner bonding, of course, and mating. And pleasant touch certainly involves activation of those mechanoreceptors we talked about before. You can tell whether someone is trailing their fingers up and down your arm, and when they're doing that, you can tell whether they have a soft textured fingertip or a rough textured fingertip, right? That's Pacinian corpuscles detecting the slight vibrational differences of soft or rough. So part of pleasant touch is certainly just normal touch sensations going to the brain, but it turns out there are also some other detectors. We actually have some other free nerve endings, which are, in this case, C fiber types, like with the slower second pain or the lingering pain. And these neurons, they go off for slow-moving light touch specifically, and tend to produce pleasant experiences. Obviously, context is a big part of this experience, like whether it's a welcome touch that's invited and expected. So, as with every other perception we'll see in this course, there's more than just the bottom-up processing of sensory receptors going off and sending a signal to the brain. A lot of our perceived experience will come from what we might call top-down processes relating to context and past knowledge and past experiences and all of that. At any rate, we're not going to spend much more time on these specific sensory receptors, but I wanted to point out that research has actually shown the pleasant touch and those slower C fiber types of pain, they actually follow the same pathways up to the brain and activate similar and largely overlapping brain structures. So there may even be some truth to the whole pleasure and pain connection that we know colloquially. Okay, finally, the last set of sensory receptors in our skin that I want to talk about here are thermoreceptors, which are receptors for, you guessed it, thermal information, meaning temperature. But to be specific, these thermoreceptors are not thermometers. They don't tell our brain the temperature outside. They only detect changes in temperature. So they tell the brain, my skin temperature is going up right now, or my skin temperature is going down right now. So rather than calling these, heat receptors or cold receptors, we might call them like warming receptors or cooling receptors, because they're feeling out that change. Now, these thermoreceptors, they are also free nerve endings, again, meaning they don't really have any specialized tip like we saw for the 4 mechanoreceptors. They just are kind of like these tree-like dendrites going out there, just raw nerve endings. And also, they are unmyelinated. They're mostly unmyelinated C fibers. So that means they send their signal to the brain pretty slowly relative to touch info, which makes sense when you think about the fact you don't really need to know that your skin is getting colder or faster a fraction of a second faster. That's not really going to change your behavior. Whereas with touch, we may need to get that info very fast in order to maintain the grip on a bottle that starts to move, or be able to, get slight, quick little changes to vibration or something that might tell us about the texture as we're moving our finger along. Okay, now when I say we have these warming detectors and cooling detectors, they are actually 2 distinct sets of thermoreceptors. So some are cold sensitive, like firing more to cooling, not as much to warming, and some are more warming sensitive, so they fire more to warming, not so much to cooling. But in all cases, they only work in what we might call sort of the normal temperature ranges, the safe temperature ranges. So here's kind of the ranges you might see for those cooling detectors, and the ranges you might see, the temperatures where those warming detectors are most going off. So of course at those low temperatures, the cooling detectors might be active, as we're getting colder and colder into the dangerous levels. This is centigrade here. But in all cases, they're only really working down to a certain level or up to a certain level, after which we mostly just feel it as a freezing pain if it's below about 25 centigrade. And we mostly detect it as just like a burning pain once we hit about 40 to 45 degrees centigrade. So mostly just in those middle ranges are where we're actually detecting it as, oh, I'm feeling like hot, I'm feeling cold. What it really is I'm feeling my body temperature, my skin is getting hotter or getting colder. So like, just for example, if in a laboratory, if we bring someone into the lab, what we might do is apply heat to their skin and then measure the axon of, say, a warmth-sensitive thermoreceptor as we turn the heat up. So take the heat, sometimes we literally just do this with a light bulb or something similar, but take the heat and get it closer and closer to their skin, getting it hotter and hotter and hotter. And these graphs to the right, you can see what happens once we get around 45 degrees centigrade, which is, that's over 110 degrees Fahrenheit. So very, very hot. At that point, the thermoreceptor isn't like changing its firing much anymore. It's not really going off more and more and more as we get more and more and more into those upper ranges of heat, dangerous ranges of heat, even though your body temperature keeps rising. At this point, you start to get some nociceptors going off, detecting sort of the damaging level of heat. Now, which part of your body do you think has the most thermoreceptors? You might suspect your hands and your feet, because that's what you first notice getting chilly when it's cold. And indeed, those areas out in the periphery do lose heat quickly, but there actually aren't as many, not nearly as many thermoreceptors there as there are in your core, like around your trunk, and your head, which might make sense if you think about the kind of rather more extreme danger when your core or your head are getting into those extreme ranges of temperature relative to the peripheral parts of your body, the parts way out there, like the hands and feet. Now, I told you thermoreceptors only detect changes in temperature, not the temperature itself. It's actually really easy to experience this yourself, and it makes for a fun at-home demo that just takes a couple minutes, so I really suggest you try this out. What you do is just find 3 tubs or buckets, or even just large enough bowls that you can easily submerge your whole hand into them. Ideally, you could be able to put both hands into them. Then what you do is put those bowls side to side. In one of the side bowls, you want to put some cold iced water. Okay, cold icy water. In the other one, the one on the opposite side, put hot water. Not boiling, not dangerously scalding hot. Don't get like a 2nd-degree burn or anything. Just hot water. And then finally in the middle one, put some lukewarm water, just a super mild middle ground between the hot and the cold water. Then what you do is immerse one of your hands in the cold icy water and your other hand in the hot water and leave them there for about a minute. Then take them out after that minute is up. Take them out and immediately put both of them together into the lukewarm water in the middle. Now, what'll happen is the hand that was in the cold water will now feel like this lukewarm water is really hot. It'll feel like it's hot water. But the hand that was just in the hot water before will now feel like the lukewarm water is cold water. So it's exact same water in the middle container, the lukewarm water, exact same water there, but it's going to feel simultaneously hot and cold. And that's because our perception of temperature only registers changes, right? Relative temperature. So warming and cooling at the skin, not absolute temperature. So the hand that was hot, when it goes into the lukewarm water, that is colder than it was before. So it'll feel cooling, and your brain will experience it as if you're in cold water right now. You'll be like, man, this is some cold water. On that hand, that's what it'll feel like. But the hand that was in really cold, icy water, when it goes into this lukewarm water, that's of course warmer than the ice water. So it'll feel hotter. You'll feel an experience of heat, and it'll feel like that's some hot water, some warm water. And so you're simultaneously going to perceive the water as having two different temperature qualities. It's a fun kind of sensory experiment you can do at home if you're interested. Okay, now I've mentioned a bunch of sensory receptors in the skin, like the 4 types of mechanoreceptors, the nociceptors, and some other free nerve endings, including the 2 types of thermoreceptors. But remember, somatosensation also includes interoception, that sense of the internal status of our body, like sensations in the internal organs and our guts. So that means things like we can detect regulation and awareness of our heartbeat, gastrointestinal contractions, respiratory changes, vascular changes. We can feel when we're having orgasm. We can feel internal pain, severe hunger or thirst, what's sometimes called air hunger, like when you're starving for air, you're not getting enough oxygen, or overfed satiety, like, oh my God, I'm having a food baby, that kind of feeling. Those would all fall under interoception. Helps us keep track of what's going on inside. So how do we detect those things at the level of receptors? And I don't want you to worry about the details here, but I wanted to at least briefly explain it. There are a variety of sensory receptors for interoception, and we call them interoceptors. Kind of makes sense, right? They're the receptors for it. And we won't spend time on them specifically, but just kind of in passing, there are basically, some of them are mechanoreceptors. For example, there are stretch receptors, similar to the little Ruffini endings. We've got stretch receptors deeper inside of us that react to blood vessel dilation. Some of them in the brain, for example, will give you a sense of headache pain. We have baroreceptors, right? Like barometric measuring devices. So baroreceptors that track blood pressure to give a sense of like dizziness will come from that. We have stretch receptors in the GI tract that'll react to gas feeling and give a sense of bloating or colic pain, and kind of react to the fullness to give us a sense of satiety when we're full, when we're satiated. We also have osmoreceptors that track fluid pressure that help give us a sense of thirst. Stretch receptors in the lungs that give a sense of respiration. So those are examples of some mechanoreceptors that track info, send info to the brain about what's going off down in the rest of the body. Others, though, are what we call chemoreceptors, meaning they detect changes in chemicals more directly. So just for example, carotid or aortic bodies inside of us track CO2 and oxygen levels. And that gives us like a sense of suffocation or air hunger or air thirst when we have too much CO2 or too little oxygen. We've also got chemoreceptors that detect toxins, and that gives us a sense of nausea or needing to vomit. So those would all be examples of interoceptors. Again, there's lots of them, but don't worry about the details. Just understand we have little detectors deeper inside our body for that stuff. Finally, There are a couple of other sensory receptors for somatosensation that we're not going to talk about right now. And that's because we'll be coming back to these in a future topic when we cover proprioception and when we cover balance, or the vestibular system. So we have, muscle, tendon, joint receptors for proprioception. These are detectors that tell the brain about muscle length or tension, joint pressure, kind of help us track position of our body parts. And we've got this whole system called the vestibular system in our inner ears, like near the cochlea. We kind of ignored it in the pictures before, but this whole other system near the cochlea, deep in our inner ears, that helps with sensing like balance and motion, acceleration. And just a final side note before we move beyond the skin and head into the brain, the skin also has photoreceptors, meaning light-sensitive cells, somewhat similar to the rods in our eyes. These detect UVA light, and they'll actually have the effect of ramping up melanin over the next day or two. But, FYI, this is only a minor benefit and won't stop most DNA damage. This is not like a natural sunblock or anything like that. And there's no perceptual experience attached to this, however, so it's not really relevant for our purposes in this course. I just want to kind of mention another detector we have in our skin. Some people have argued that actually this is probably before creatures developed eyes. This may have been a way to detect, to sort of kind of track chronorhythm, track like daytime, like whether it's day or night. So these might be detectors for more automated processes without having an actual experience or the details of light that are necessary for vision. Okay, anyway, let's just summarize all the somatosensory receptors that we've talked about. The things that transduce input that hits our skin, for example, or input inside of us, and sends a signal to the brain that turns it into neurons firing. So we've got the mechanoreceptors, that's Merkel discs. Those are really important ones, and especially for like static touch, static pressure. Meissner corpuscles, Ruffini corpuscles, and then those Pacinian corpuscles, I said, are really important for texture. They're really important vibration detectors. Okay. Then we've got nociceptors. We talked about two types. The fast ones for initial pain, those are A delta. And then the slower ones for that secondary continuing pain, those are C fibers. And also some nociceptors are for itch, right? Also some just subtypes of C fibers for itch. Of like the histamine, the mosquito type. Okay, then there are similar kind of free nerve endings for pleasant touch. We also saw free nerve endings that help us sense warming or cooling, so changes in temperature, and those are our thermoreceptors. And then we've got the interoceptors, which we didn't get into we don't need to know the details of those too much, but we have detectors for internal status, our organs, and so on. And again, we skipped over the stuff for proprioception and for the vestibular system or balance. We will do those in a future topic. So finally, to end this video, I just wanted to suggest one other at-home demo that you can use to experience the function of your Pacinian corpuscles. I mentioned before, most of our perception of texture, especially when moving your hand along like a surface or an object, comes from vibration stimulating those Pacinian corpuscles. So for this demo, you'll just want to grab a pen or some other rod, like a little wooden dowel, something like that, and then find a few smooth or rough surfaces. This could be like just a smooth wooden table in your kitchen, maybe different walls, the surface of a towel, some sandpaper would be really good, or whatever you can come up with. Maybe just the little circles of metal along the side of a notebook, if you have that type. And then what you'll do for this is just close your eyes. So keep your eyes closed for this whole thing, and then hold your pen or that dowel very lightly and just lightly drag it across some different surfaces. And while you do that, pay attention to your sensory experience. Do you perceive the texture? Is it rough? Is it smooth or whatever? And then more interestingly, where do you perceive the texture? For most people, when you do this demo, the perception is not of some vibrations happening in your finger. The perception doesn't really seem to happen at your fingertip when you're holding the pen and dragging it along a surface. It's not like you're feeling the texture at your fingertip, but rather projected out onto the object or the surface itself. We seem to sort of directly perceive, to directly experience or feel the texture of the object. in this case, through the tool. Even though our skin isn't touching the surface, it's just getting vibrated from the pen, vibrating along the surface. But when the wires from those Pacinian corpuscles send a signal off to the brain, we're used to perceiving and directly experiencing texture, not the vibrations that come from moving skin along that texture. Something just feels rough, it doesn't feel vibratey. Anyway, in the next video, we're going to follow these somatosensory system wires as they go up into the brain.